Okay. Good morning, everyone, or should I say hi, everyone. We never know where people are. It's 11:15 in the morning here in Rio, and my name is Luiz da Costa. And on behalf of the local and the international organizing committees, I would like to welcome all of you to the workshop, our workshop on the future of data centers and eScience institutes. This workshop was organized to celebrate LIneA's 10th anniversary and has the support of the National Institutes for Science and Technology of the Universe, is a program funded by the federal government, Brazilian federal government, and also the funding agency FINEP. And those are the logos that we have here on the site. But before I introduce LIneA, in my opening remarks, let me make a couple of announcements that might be of interest to everybody. First of all, just to remind you that you can go to our site. There is a Slack channel for this workshop, and there are instructions where you should, what you should put there, how to link, and how to the information that we want to use. You should post your questions in the Slack channel, appropriate Slack channel for day one, day two, etc. Also, you can make suggestions for issues that you'd like to be debated on the last day. On Thursdays, a REPAS session. It's a 1 hour session with all the members of the International Organizing Committee and roundtable. Also, we've been asked, all talks will be recorded and will be made available at our site in the following Monday. So that gives us time just to arrange everything. And there were a couple of changes in the program. The most important one is this today's last presentation in the morning session actually has been moved to the end of the afternoon session because of a conflict, a last minute conflict. So let me now try to introduce LIneA. LIneA started unofficially. Well, first of all, LIneA stands for Interinstitutional Laboratory of E-Astronomy. And as you may tell, the name tries to capture its mission of enabling science to help handle the new projects that are generating large volumes of data. It started unofficially back in 2006 when a group of Brazilian scientists joined the Dark Energy Survey. And the goal was to provide technical support to these scientists and their students and postdocs. In 2008, another group joined Sloan Digital Sky Survey, and we figured that we needed to have something more robust, and so the LIneA was created officially in 2010 with the support of 3 institutes from the Ministry of Science, Technology, and Innovation, and this involving the institutes in astronomy, which was the National Observatory in Rio, Computer Science Institute, which is the National Lab for Computing, Science Computing, and also Network, which is called RNP, which is the equivalent of, I believe, Internet 2 or ESNet in the States. And our funding has come from a variety of sources, including more recently, this is a special long-term program to fund strategic projects, the one I mentioned at the beginning. Now, LIneA provides technical support to teams involved in a total of 5 international collaborations. In fact, the Dark Energy Survey, the Sloan Digital Sky Survey, DESI, LSST, and also this French-Brazilian collaboration to study the solar system. The support includes computing infrastructure, software development, and a variety of IT service. Over the years has developed its own dedicated infrastructure, which now consists about a variety of processing clusters with a total of about computing power of about 25 teraflops. We have a total storage of about 1.5 petabytes. We have databases for the mirror site of the Sloan Digital Sky Survey using Microsoft SQL. We also have Postgres for the dark energy survey data. We have a virtual cluster of virtual machines for hosting all our service. And we have optimized a sort of DMC system to increase the performance of the data transfer. Our machines are dedicated and are located in Petrópolis, which is a city about 60 kilometers away from Rio, and this data center from this National Lab for Scientific Computing called LNCC. We are next to the Brazilian supercomputer, Santos Dumont, which has about a computing power of about 5.1 petaflops. And actually, we also have access to this machine. So we have all of our computing power next to each other. Our services include, first, the data repositories. We have kept this long mirror site from this long since 2010, since the data release 8. We also have developed the interface for the dark energy survey with the data hosted at NCSA, but now we actually transfer DR2 here to Brazil, so we will also have a mirror site here in Brazil for the public release, DR2. And we have right now, for people that are affiliated to these projects that we support, several services: Jupyter Notebook, access to our computing clusters, and a number of other science platforms that I will mention later. It is our intention at the moment to actually make this available more broadly to the global community, in particular the Brazilian astronomical community. We have also intense program of software development, which has been used over the years as sort of in-kind contributions to these various projects. We have developed a portal that combines data from DS and the Minor Planet Center to predict events of occultation. This has been for this French-Brazilian collaboration. We have also developed a platform to visualize the megacubes that have been obtained from the MANGA survey, from this long digital sky survey, not only to see the data, the megacube, but also the derived products. So over 30 maps of different quantities that have been derived from the megacubes. So this is for this long digital sky survey. But our major effort has always been for the dark energy survey. So first of all, we developed, actually we have developed other things, but we also did an interface for reducing data from the pre-cam in the old days. But we also we produced this platform to evaluate, to assess the quality of the image that were being obtained from DECAM, both for use of the dark energy science collaboration, but also for the community at large, that CTIO using the DECAM. So this we call Quick Reduce. More recently, we have developed what we call LIneA Science Server, which is a platform to visualize images in catalogs and make queries to the database. This has been up at NCSA since 2018 to access the first day public release that DS did a couple of years ago. And now we have upgraded a bit for DR2, and also we're installing here in Brazil. And finally, the more ambitious projects has been by far the Dark Energy Survey Science Portal. The Science Portal is a web-based system from which workflows can be submitted to our computing cluster and monitor. Each execution is registered in a database, an associated database, along with the configuration files used, the input data information, and the results that come out of it. This allows us to keep track of the history of the executions of a given pipeline, enabling the user to revisit and compare the results of different runs and to trace their provenance. So the idea has always been that to facilitate the life of the user, of the scientist, to have this end-to-end pipeline. So we started out installing the data that's was being produced at NCSA, the basic extractor catalogs from the quaded image, the mango mask, and other information like bed region maps, foreground maps, which are produced during the process of data reduction. We bring this here to Brazil, we install that in our infrastructure, and then we execute these pipelines. First is stage of data preparation, where we basically try to add value by computing photosys and all the processes that are involved in producing these photosys. We also compute galaxy properties, classify stars and galaxies, and produce systematic maps, which also lead to depth maps. And from that, we actually produce VACs, which are science ready for different science applications, which in turn, feed the science workflows and eventually can actually go into cosmology. This is the user interface. It's a kind of old interface. This was developed back some 10 years ago, but essentially is the user has access to the different stages, and so he does not have to handle the data at all. And also, it can choose all the input data that is pertinent to that specific pipeline. Our pipeline concatenates all these workflows dealing with different stages of the end-to-end process that goes from these original query catalogs produced at data reduction phase to this different science analysis. The nice feature about it is that we can keep control of all processes, of all pipelines that are within the framework. And this is especially neat and useful, I believe, when we are trying to work in these big projects involving teams spread geographically, and you would like to try different things and compare different results. So this is the reason we developed this. And the nice thing is if you select a specific pipeline, for instance, the one that's shown here in red, which is a sort of a cluster finder that we have developed for DS, and we are now extending also for LSST, you see that there was something like 35 runs done with this pipeline. So you can actually go and follow them all have information of all these runs that were processed with these pipelines. And you can check all the configuration files used, you can check the results. And if you want, you can drill down a little bit further and actually see all the processes that had a bearing in the input data for this catalog. So basically, this is a cluster finder that had a VAC, and this VAC was produced by a star galaxy separation process, and in turn, was added a photosy that was computed using the information of the training files, the spectroscopic sample that you have used, and so on. So this is the neat thing about this integrated system. Now, the science portal was adequate, I would say, for the dark energy survey. Unfortunately, the way we have implemented that definitely does not scale to LSST with 40 times the volume, data volume we handle with the dark energy survey. So there were a number of shortcomings that we had no time to address as we were trying to develop and operate at the same time. But definitely we're using old technology, which definitely should be integrated, should be upgraded. We had the system we built was kind of hard to integrate the external codes, and we find that that's a key for the future to be able to have collaboration of external scientists. We had other more technical problems like inadequate orchestration, which led to poor performance, and etc. Since we are in a transition period and we are looking forward, and we are planning now to host an IDAC for LSST, and we would hope to have all this lessons learned from the dark energy survey move forward to the LSST and to be able to support the science of the members of the Brazilian participation group and the local community as this data eventually become public also. We definitely have this motivation to develop version 2.0 of this portal. Definitely changing a lot of things from the lessons we learned, but trying to preserve the basic concepts of having this isolation of the user from the handling the problems of data transfer, etc., and also the possibility of checking and comparing projects, sharing with groups, sharing with individuals, sharing with the science work group. So that's, we need to rethink our approach, and this was actually the motivation for our workshop. I will end here, and again, I like to welcome all of you and wish that we have a great meeting. And let me now hand over the microphone to the chair of the session, which is George Beckett, and I'll do that by stopping sharing my screen. George, please take it away.
Thank you, Luis. Can you hear me okay?
Fine, thank you. That's
great.
Perfect.
So I'm looking at the Slack channel. I wasn't sure if anybody wanted to ask you any questions on your presentation. There were lots of interesting things in there. It's the Slack channel you wish people to use to ask questions, is that right?
Yeah, that's right.
Okay.
Day one session. Well, I mean, you shouldn't worry. You should just check the Google Doc. I mean, we have people copying and pasting the questions, okay?
Okay. I don't see any questions just now. I think that was a very good introduction to the workshop. So I suggest we'll move on to the next talk, if that's okay. And maybe if there's more general questions, we could come back to them later on. But our first speaker for this session is Simone Campana from CERN. He is the Deputy Project Leader for the WLCG, the Worldwide Lattice Compute Grid. So we're starting on the large scale. I'm sure many of you are familiar with WLCG already. It is the distributed computing infrastructure that supports the LHC. And they have some significant challenges on the horizon because they're planning an order of magnitude expansion of WLCG in the near future. And Simone is going to tell us some more about, I guess, the success of WLCG to date and the plans going forward. So I'll hand over to Simone.
Thanks. I think I'm now sharing my slides.
You are, yes.
See them
we can
full
see
screen.
your sort of. We can't see them full screen. We can see them within your PowerPoint window. We can see them full screen
even now.
Yes, that's good now.
Okay, good. Okay, thanks. Yeah, so this talk is about WCG. As you said, it's a distributed infrastructure for large-scale scientific computing. I'll go to the next slide. I think I don't need here to explain in this forum about the expansion of the universe, but what I want to mention in here is that at CERN, in terms of fundamental research, our main activity is really to try to recreate the initial conditions after the Big Bang, and we do this through colliders, particle accelerators, and in particular colliders. So we accelerate particles at very high energies and we collide them and we look at the outcome of the collision to try to recreate the same energy density conditions as the early universe. This is our largest installation in terms of accelerating machines. It's the Large Hadron Collider. It can accelerate protons and heavy ions. It's a 27-kilometer ring. It has superconducting magnets to bend particles and accelerating cavities to give them energy up to 14 TeV as a center of mass energy of the collisions. I take the opportunity also to mention that while we collide bunches of particles at very high frequency, on the order of of 40 megahertz, so 40 million bunch crossing per second. Actually, what we are looking for is really rare events. So we have a probability of having something new or at least interesting at a level which is much less than the millihertz. So you have many orders of magnitude between the bunch crossing ratio and the probability to find something interesting. This is just a few pictures. You have the Large Hadron Collider, the tunnel, and the machine. On the left hand side, on the top, you have a diagram and a real picture of the Atlas detector, and you have a real event from the CMS experiment with the Higgs particle. When I refer to detectors and experiments in the LHC, there are 4 experimental areas. Each one hosts an apparatus, which is a detector. It's the big microscope, basically, that detects the outcome of the collision and that physicists use to reconstruct the events. Because of what I said, so that we are looking at very rare events, our data, the chain of data retention and data processing really has 2 steps. The first one is what we call the online processing. So out of the 40 million events a second that the LHC gives to us, we filter very quickly, so in real time, the ones that are worth retaining for future studies. So out of 40 megahertz, we retain something like 1 kilohertz of interesting physics, going through a couple of steps. The first one is a hardware trigger, and the second one is a software-based trigger, so based on algorithms. So our first challenge is, of course, going from big data to useful data. Those are the data that we really retain and we store, and that we analyze for the forthcoming years, while everything that is rejected on the top, so in the red part, is practice gone forever. This 1 kilohertz of event, it's still quite large in terms of volume and complexity. One event is a megabyte. Multiply this by a kilohertz, and you consider that we collect events for something like 7 million seconds in a year. You have something for the 4 experiments of 50 petabyte of data per year. Those data are reconstructed, they are calibrated, they are compared with Monte Carlo simulations, and then out of this you have the physicists that do the data analysis and hopefully find something useful. And this blue part is what we call asynchronous processing, and this happens again and again because you can have better calibrations, you can have more sophisticated Monte Carlo simulations, you can have new analysis techniques. Back in the days, which means in the previous century, we would do all the needed processing, all the processing of the data at CERN. This was the model before the LHC. But for the LHC, the demands in terms of compute and storage infrastructure were so large that we decided to go really for a federated model based on network services in a way that we could group national and international activities into what is today the WLCG, so the Worldwide LHC Computing Grid. So this is really, beside an infrastructure, is really an international collaboration. The aim is to distribute and analyze the LHC data. The different data centers, they have their own policies, and what we do is we integrate them in order to provide to the end user physicist compute and storage resources that look like into a single infrastructure. Beside this model, we have a hierarchical structure. So CERN is the tier 0, has a special role. First of all, data recording, reconstructing the data, and then distributing the data to the other sites. The tier 1 are large national facilities. They also have permanent storage. They do reprocessing of the data and some of the analysis. And then tier 2s are mostly universities. They participate to the simulation, and that's where most of the physicists are. So this is where a lot of the end user analysis happens. If you want to know about some of the numbers, today we count 161 sites in 42 countries, something like 1 million CPU cores, an exabyte of storage, and the network links, which vary between 10 and hundreds of gigabits. This is just a map which shows the geographical distribution. You see that is really across the 5 continents. CERN, as I said, has a special role in this. It receives the raw data from the experimental areas. It archives them on tape for long-term preservation, performs the needed data quality assessments. It reconstructs the events into a format that is suitable for the analyzer. And then it also exports this data to the other sites, to the other WLCG centers. The raw data is archived at the tier 1 facilities as well as CERN, so that we can keep 2 copies of the data, because this is the precious one that we don't want to lose. And the reconstructed data is further distributed for analysis. This is a plot that shows the activity writing and reading from the CERN tape archive. I take the opportunity to say that the LHC physics program is really organized in runs. So those are periods of data taking, are about 3 years, and they are interleaved by what we call long shutdown periods. So those are periods roughly 2 years. They can be 2 and 3 years. This is when the major upgrades to the accelerator, the detectors, and the computing system happens. And you see here a structure of runs in writing to tape. Most of what we write to tape are the raw data. So of course, during a shutdown period, you don't write much. But if you look at the plot in the bottom, this is the reading activity. You can really see that we don't really know a structure of the structure of the long shutdown in terms of reading, which means we process data continuously despite the long shutdown. Actually, the long shutdown are the periods in which you do most of the processing, because of course you're not busy with all the activities which are related to data taking. This is about the evolution of the computing model. This was the initial computing model, the last century. At that time, the model was really based on the uncertainty over network performance. So we believed that networks were a scarce resource, and one had to use it very wisely and really make sure that you would transfer data over very well specified paths and not in a more flexible way. The focus really was on distributing the data globally to compute resources in a hierarchical structure. So from CERN, the data was going to the tier 1s, and each tier 1 was distributed the data to the tier 2s of its region, not other regions. And every center, every data center would run compute and storage service. So you move the data into that center and you analyze it through the compute capacity of that center. There was no concept of storing data somewhere and accessing it from somewhere else, that nowadays with all the clouds, etc., seems to be a granted principle, but back in the days definitely was not. And the tiers really had predefined roles, as I said, the tier 2s for simulation, tier 1s for reconstruction, etc. Now this quickly evolved. It evolved quickly because, in fact, the initial assumption was wrong. The network was not really a scarce resource. Actually, was one of our greatest opportunity, because our use case gave the opportunity to the research and education network to increase the network capacity by having to support a challenging use case. So the WLDARA network connectivity between our centers increased between a factor 2 and a factor 3 since 2017, which was the end of the last run, but it increased also more than a factor 10 in the last 10 years. And this is much larger than the natural increase of disk, CPUs, and tape for the same price tag. So our new model became really more network-centric. You see here, we transfer between 30 and 50 gigabytes a second of data worldwide, and this plot doesn't really know about run periods and long shutdown. I mean, the activity occurs more based on the kind of workflows that we are executing, whether we are reprocessing the data or whether there is some ongoing large Monte Carlo campaign, rather than having the pace of the data taking periods. And this is shown in another way if you look at how much CPU is used in WLCG. The units here are HEPSPEC 06 hours. A modern core has something like 10 HEPSPEC 06 as a benchmark. So we use something like 1 million cores simultaneously, and the utilization keeps increasing. And again, you don't see a structure here which has to do with long shutdowns and runs. We really operate 24/7, 365. We also monitor 24/7, 365. We monitor continuously and we review regularly the performance of the sites. We have targets that are specified in the memorandum of understanding we sign with our funding agencies, and we review regularly the performance targets against the MOU, the performance against the MOU targets. Also, this definition of tier changed. As I said, initially the tiers, they really had a specific function, but today, because of the flexibility that we have in transferring data in a full mesh rather than hierarchically, also our tiers and the utilization of our tiers became flexible. So now tier ones and tier twos, they both run a mixture of workload depending more on their capability rather than whether they are a tier one and a tier two. And you see here a plot of utilization for a tier two. Every color is a different kind of activity. There are 5, which are the major ones. So you see this tier 2 basically runs pretty much a mixture of anything depending on the needs of the experiments. All right, so this is all good. And then the question is, what is this talk about? So we are about to face an unprecedented challenge. The LHC, so the accelerator, is going through a major upgrade in something like 5 to 6 years from now. This is what happens in our long shutdown 3, and the phase that comes afterward is what is called high luminosity LHC. And also the detectors, so the experiments, they go through a major upgrade to cope with the new conditions from the LHC. What is this major upgrade? Well, high luminosity LHC will deliver 10 times more useful events, more interesting events per unit of time. And those events are going to be bigger in volume, let's say, and also more complex in structure. And in the next slide shows what complex means. On the left-hand side, there is an event collected in the last run. It's a very large event, by the way, something with a lot of particles interactions. We have 78 reconstructed vertices. And on the right-hand side, this is a simulation of what an event will look like at high luminosity LHC. So it's something like 200 reconstructed vertices. And we have not only those complex events, but we have 10 times more of them. So it's a double challenge, if you want. Back in the days, you would simply sit down and wait for things to happen, because thanks to Moore's law, every 18 months for the same number of US dollars, you would buy twice the compute capacity. There is still a bit of this effect. You know, the cost of hardware keeps decreasing. You have this plot on the bottom, which is what we pay at CERN for CPUs, for example. It keeps decreasing, but is not as steep as before. And what is worst is really that in general, the trends are not driven by technology evolution anymore, but the trends are really driven by market and revenues. And you know, even some of the media we relied on for long, they have a future that is not really certain. For example, that was an announcement from a few years ago from Oracle about not supporting anymore enterprise drives. So there is in fact, a general loss of long-term predictability. And, you know, high luminosity LHC happens 7 years from now, 8 years from now. So we really are looking at a long time span. So, of course, we are looking into how severe the problem is, or how challenging the challenge is. So we do not foresee an increase in funding. Our funding agencies were really clear. We can rely pretty much on the same amount of funding every year, but not more than that. So this is what we have to live with. Technology gives us some increase in the amount of compute and storage capacity we can buy. This is what we see here between the two solid lines. But when you see how much, for example, compute capacity we will need in high luminosity LHC, so in the timescale of 2020 to 2030, we need more than we can buy today. You can see a lot of those lines are above what we can buy with a flat budget model, except one that really fits in between, which is what we foresee it can happen if we successfully go through an aggressive investment in R&D in the next years. So our infrastructure will need to evolve also. It's not just in terms of technology, but also in terms of policy. We have to watch for long-term sustainability. We are operating this infrastructure since 20 years now. Has been very successful, and like everything which is very successful, you have a tendency not to change it, but you have to operate it for the next 15 years. There are now more opportunities, more technologies that you have to fill in, that you can leverage. So you have to modernize and make sure that you can sustain your infrastructure. And the funding agencies, they are still happy to spend, but they want to see their investment benefit not just high energy physics, but multiple sciences. So where is this R&D? Well, first of all, today we can get opportunistic use of many types of compute. One example is high performance computers. Those are very large machines. You can get access to a fraction of it. Then you can get hold quite a bit of compute capacity. So we have to make sure that we can integrate those facilities transparently into our infrastructure. We can use them. And large part of this challenge is really a software challenge. You see on the right-hand side on the bottom, the HPC, the Summit HPC at Oak Ridge National Lab. This comes with about 10 petaflops of non-x86-64 CPUs, but the vast majority of processing capacity comes in the form of GPUs. And our code has really been developed past 20 years and has a lot of legacy in it. So it has to go through a major redesign, re-engineering to be able to leverage new architectures and in particular accelerators. So a lot of this is really a software problem. That's why we invest a lot now in software performance, software modernization, innovation, portability. This is one of the key areas for high LUMI LHC. And it really needs investments upfront. Those are some of the initiatives that we have today that go into this direction. One on which I would like to point the attention is the HEP Software Foundation. This is really an initiative that tries to facilitate the cooperation and common efforts in HEP software and computing, but they also span beyond the scope of high energy physics. They try to reach broader communities. A second place where innovation is needed and where R&D investments could bring benefit is the way we organize our facilities and our data. As I said, back in the days, every site would offer storage capacity and compute capacity. Thanks to the network services, this is not necessarily the case anymore. Particular storage is a very challenging service to support because it is responsible for the long-term retention of the data, and not all our sites, they have the same level of expertise and skills of the administrators. So we are looking into a model where we have a fewer number of facilities operating the storage services. We also, therefore, have less data replication, but then we have an heterogeneous set of compute facilities. It can be grid compute, it can be cloud compute, it can be HPCs, it can be also volunteer computing, which do the data processing. And of course, now you have the challenge to bridge the compute capacity and the storage capacity. And the way we are looking into this is by a network-based content delivery and caching service. So this is part of the R&D we are looking at. And finally, in terms of sustainability and open shared infrastructure, the idea is that we have to move into a direction where our facilities are not specific to us. So we use solutions that can be broadly adopted by other sciences and other communities. So we are now moving away from everything that in the past was HEP specific. One of the main challenges, for example, is in the evolution of the authentication and the authorization system. It has been based on X509 for a long time. There are now more modern technology, token-based authentication systems, which can fit better the structure of modern web services. And then the last theme I want to touch, this is data from 2017, probably worth an update, but it shows that while probably LHC is one of the largest sciences, it's definitely the largest at the moment in terms of data volume in high energy physics, probably also astronomy. There are other challenges, there are other sciences that will be comparable to LHC, to high energy physics in the horizon of the next decade, and SKA is brought here as an example. I think we don't have to stick on those numbers exactly, but it's just to say that there are going to be several major players from high energy physics and astronomy in the next decade. And therefore, it makes, of course, sense to establish partnership and collaboration between those different research streams and projects. So when we had the European Strategy for Particle Physics, the Open Symposium in Granada 2 years ago, it was good to see that several of those sciences really provided input in form of white paper to the process, wishing to collaborate with high energy physics for future software and compute services. And we also have an active collaboration between CERN and SKA on extreme computing. And of course, as WLCG, we have partnerships with non-LHC experiments. Example is the Bell2 and Dune experiments, which are now observers. They are associate members of WLCG. So there is here really an opportunity to collaborate across different projects and sciences on the same infrastructure. And at this point, I would tell you what escape is, but this is really the subject of the next talk. So I'll leave this to Ian to explain. And this brings then me to the conclusions. WCG is an organization that provided shared distributed infrastructure for the LHC experiments the last 15 years at least. The computing models and the infrastructure and services evolved, they changed, they adapted with time to the evolving landscape. We have in front of us an unprecedented challenge in terms of scale and also in terms of sustainability, and there are other data intensive sciences that will coexist in terms of challenges with LHC, very similar use cases on the same time scale, and they will share the majority of the same physical resources. So there is an opportunity here to share policies, to share tools, to share expertise, to share services, and when plausible, also share resources for the benefit of all those sciences. And I think this is my last slide. Yes.
Thank you very much, and very good timekeeping. I hope everybody will do as well as you. We have a couple of questions that have been put into the Google Doc, which I'll try and read out for you just now. So Robert Nikuta, I hope I've pronounced your name correctly. He noted there was a clear drop in processing at around about March 2021, and questioned if that was possibly related to the onset of the coronavirus pandemic. I guess this is one of your earlier slides when you were talking about progress over the last 10 years.
I think it refers to this, I guess. This is the drop.
Yeah, okay, that makes sense.
Right. It's an excellent question, and of course we looked at this in details because the timing looked very weird. In fact, it is not, and not completely. You see, in fact, here there is one of the 4 LHC experiments that is transferring less data. The other experiments, they continue as they are, and this experiment, this is the the experiment, as I said, during the shutdown, the experiments, they evolve their computing model and their services. So this experiment in particular moved to a much more condensed data format for analysis. So they can capture in much smaller, in a much smaller format, the same information that before needed almost a factor 5 more space on disk, and therefore, when you move around this data, it needs a factor 5 less bandwidth for transfers.
Okay,
so
so that's
it is
actually
a bit coincidental, but
yeah, it's one of the
it
aggressive R&Ds you were talking about, I guess.
That's correct. And in fact, this experiment pioneered this. The other experiments, especially the blue one, which is the other major player, as you can see, has been looking into this. They are commissioning the same solutions in the next few years. And if you look at the next plot, you see here the amount of CPU delivered. You see there is no drop. So in fact, we continue processing data. We just move them less around.
Okay.
I think that's what you want.
I'll try and squeeze 2 more questions in, if that's okay. JJ Kivlars, sorry, I hope I've got your name right. As we move to the era where multiple places are producing exascale, will the network be sufficient? This was a question I was wondering, actually.
Yeah, this is it's being looked, of course. For the moment, high energy physics has been a major player. The reality is that when you discuss with the funding agencies, and in particular with the network, the research and education networks, they find our use case so challenging that they are ready to invest into it. It's not just in the form of capacity, but there is a really network R&D that you can do to squeeze out of the available capacity more bandwidth for different sciences. So there is a large set of those initiatives that are going on. And if, for example, you look at the ESNet, this is really a good chunk of what they're doing today for the US, but also, you know, they connect the US with Europe for our use case, for example. And I guess this is the same for other sciences.
Thank you. And I'll ask one final question on behalf of Andreas Vicinec, who asks, do you have a study about the impact on climate from all this computing? So that's a slightly orthogonal question to some of the previous ones, and maybe a tough one to answer in short
there
time.
are ongoing, there are ongoing studies, and there is more awareness, of course. Modern data centers are thought with this not just in mind, but really as a prerequisite. One of the examples is we are now about to build a new data center at CERN, and this really has in mind to have a very good POU, so not to waste too much energy, for example, into cooling. We have heat recuperation, and this is built into the tender. So the idea is that by building a new data center and even providing even more capacity, we actually are more environmental friendly because we consume less energy for what we need to do. And this is something that we brought to the attention of the international community. This is something that is being discussed more and more also at conferences and workshops. It's a very good point.
Thank you very much. It's very difficult in Zoom to actually thank speakers properly, but there is a reaction button where we can all clap. So I suggest we do that. And maybe at the end of the session, we all open our mics and clap properly. But thank you for just now.
Thanks.
And there may be other questions. If you have a look at the Google Doc, it could be you could discuss those offline. That would be great. So our second speaker, as has already been previewed, is Ian Bird from LAPP in France, who is the technical coordinator or a technical coordinator for the ESCAPE project. This is a European Commission funded S3 research infrastructure. So without further ado, I'll hand over to Ian to tell us all about ESCAPE. Thank you.
Hey. Yeah, so I hope you can hear me and also see my screen.
Yep, and yep.
Yeah. Okay, so I'm going to talk about the ESCAPE project, which somebody mentioned. So ESCAPE is a project in the context of the European Open Science Cloud, which itself is a European Commission response to the member states' policy on the uptake of open science. So the EOSC will be a cloud for research data in Europe, intended to allow more open access to data. And it basically federates existing resources across national structures, infrastructures, the science research infrastructures, and the intention is to allow researchers and citizens to access. So there was, as part of this EOSC movement, there was an initiative to bring the sciences together. So there was a funding call a few years ago to build the science clusters.
Ian, we cannot hear you.
Is it possible something's interfering with your mic? It sounds like, have you got a mic on your clothes or something that's rustling?
No, the microphone is distortion.
I think we might be having mic problems. You're very difficult to hear right now. Ian, do you have an option of a different mic? We can't hear you at all now, or at least I can't hear you at all.
Has that made any difference?
Oh,
yes.
That's much better.
Okay.
We're in Dolby Stereo. Brilliant. I'll mute and let you carry on. Thank you.
It's interesting because I've gone to the worst microphone. So
okay, good.
So ESCAPE itself is one of, so as I said, there are five of these, sorry, I need to go back and somehow right, there we are. There are five of these science clusters, one on environmental sciences, one on life sciences, one on social sciences, photon and neutron sciences, and then ESCAPE, which is astronomy, astrophysics, particle physics, and nuclear physics. And ESCAPE itself brings together these communities with different complementary skills and experiences. So in particular, astronomy with a virtual observatory infrastructure, and high energy nuclear physics, which has the sort of very large scale data management, large scale distributed computing expertise, which Simone just talked about. So the intention is that this collaboration of all of these different infrastructures builds on the synergies between them, brings together all of these overlapping and complementary competencies, and also the authorities of the national stakeholders. And we recognize that many of the communities that are involved in ESCAPE are starting to be and will be in the future data generators at the exabyte scale, and also are really innovating in the area of data management and are communities that typically push this state of the art. And all of us, both observatory type and facility type operations, require this sort of global view. These are international collaborations, although this is a European project, there's a dimension outside of that. They all require open access to their data, and in particular, the long-term curation of that data and sustainability of the whole infrastructure. So this is something which is important and common across all of these communities. So this gives you an idea of the communities which are in ESCAPE. So you see astronomy, astrophysics in various wavelengths, radio, visible light, gamma rays, and then you have cosmic ray neutrinos, gravitational waves, and the accelerator-based facilities in nuclear physics and in particle physics. So the project itself, in brief few words, is 31 partners, of which 2 are small businesses. 7 are the so-called ESFRI projects and ESFRI landmarks. So ESFRI is the European strategic research infrastructures. Or proposed as an S3 really means that the national funding agencies take a lot of notice and they get preferential funding treatment. So it's important to have that recognition. And that there are 2 pan-European international organizations also as part of the consortium. This is CERN and ESO. And then we have EGO and the JIVE ERIC, and ERIC is a European research infrastructure. And these are supported also by these broad consortia, these European consortia of the national funding agencies in astronomy, particle physics and nuclear physics, which is very important because the chairpeople of these consortia are actually on the ESCAPE advisory boards. So the project is 16 million euros. It started at the beginning of 2019. And it's now 4 years. It was 42 months, but we had an extension due to delays caused by the pandemic. So Simone mentioned the importance of the European strategy for particle physics. I would just note here that there are several references to the importance of this kind of collaborative activity between the communities. And in fact, it points out ESCAPE and the HEP Software Foundation as important common coordinating structures, which help coordinate and bring together these activities. So the work program of ESCAPE is clustered around 5 technical work packages. One on a scalable federated exabyte scale data infrastructure. So this is what we're now calling the data lake. This is intended to be a data infrastructure for all of these large sciences which are involved in ESCAPE. And of course, it enables connection to compute and storage resources, and I'll come back to that in a minute. There's another action on the software repository, and here software is an important piece of data. So data in EOSC terms not only includes the research data, the data we acquire with the facilities, but it's also artifacts such as software and publications and other things which are coming out of the activities. There's a work package on the virtual observatory, which is really bringing the virtual observatory into the EOSC context. There's a work package on science platforms. This is not replacing the existing workflows that the various experiments have, but it's introducing new ones and platforms to support those, and in particular, looking at global platforms to enable transversal workflows, such as multi-messenger astronomy. And there's lastly part of the communication work package, there's an aspect of that which is dedicated to citizen science. So enabling the access to the data lake for citizen scientists on certain types of data. So the various contributions to the EOSC you can see here, and each of the 5 science clusters has this type of set of contributions. And in the interest of time, I'm not going to talk further about that. It just is the way the various work packages are contributing to the goals of the EOSC. So if I talk about the data infrastructure, so this is the ESCAPE data lake, which aims at delivering a prototype of the entire data lake concept, which is really a common storage infrastructure for all of the experiments which are part of ESCAPE. It provides a level of global data management, the orchestration of that, delivers and enables open access and fair data services. It implements trustable data repositories and the long-term sustainability of the infrastructure. And it's the whole thing is driven by the requirements of the science project. So the science projects are really important here in defining the way that this goes. So this is also the diagram that Simone showed, but really the importance here is that you have a storage orchestration on top of distributed storage. So the idea is that you have policy-driven data replication and distribution, and you're kind of immune to the comings and goings of individual pieces of storage. So as long as you have data which is replicated, a storage service can disappear and be replaced by another, and the policy will automatically make that replication for you. So you can think of this as a sort of internet-wide RAID system for your data, which gives you the ability to have a long-term sustainability of the infrastructure, which doesn't really depend on a single storage instance. That then sits on top of a content delivery mechanism, which is enabling the remote servicing of data to the heterogeneous compute facilities, which could be clouds or grids or whatever. So this relies on good networking, the ability to do caching, streaming, and so on. And the point is, it really hides the complexity from the science user of how that data is really accessed. So there is a functional data lake as part of the project. This is something which has been realized over the last year. Currently has about 10 functional endpoints, which you see listed there. What's making this work is the orchestration layer is the so-called Ruscio software, which is a product of the Atlas experiment at CERN, but is now being used not only in ESCAPE, but also by several large-scale experiments to manage their data. So this is really a data management service, and implements all of these policies and so on. Underlying that, you have some file transfer service, the FTS here, which implements all of the point-to-point and third-party data transfer under the covers. There is a federated authentication authorization, or token-based, which is where the world is going these days. And what's important here is that this system sits on top of many different types of underlying storage services and storage systems, and you see some of them listed here. And it's also independent of specific types of data transfer protocols. So it's working with HTTP, it's working with the old grid FTP, and it's also working with the high energy physics specific protocol, which is called XRoot. And all of these give you equivalent data transfer rates, and different communities can use different protocols as they need. So at the end of last year, there was a sort of fairly major data challenge which happened. So all of these experiments listed here injected their data into the data lake, and demonstrated various uses of that, various workload driven activities, and you see some of those together. So all of these are using this common data management infrastructure, and the plots just give you some numbers in terms of files and the amount of data that was there. So some of these numbers are fairly modest, but nevertheless it showed that all of these can use the same infrastructure, which is, I think, quite important. Moving on to another aspect, which is the software repository. So the idea in EOSC is that the repositories are enabled, basically the science communities are encouraged to publish all of their tools and software into the broader EOSC so that they can be made available to other communities. It's something that, of course, we've tried to do in each of the communities, but now we're looking across them. And so, these software repositories are kind of the starting point from that, and they will be accumulated into a more general EOS catalog visible through a sort of top-level portal. So the work that's done in an astronomy community or high energy can be viewed within ESCAPE by the others, but the intention is within EOSC that they're available to any other science who is interested in them. Within ESCAPE, the deliverables of this activity is really to establish a foundation for the community, expose and share the software within the EOSC, or the ESCAPE version of the EOSC catalog, and provide training and guidance to the users to enable that. And this is built on top of open source and existing tools. This is not a development project. It's really integrating what exists and bringing it together in a coherent environment. So you see some of the examples of parts of the service here. So the repository itself is built on Zenodo. It uses GitLab as the development platform, and so on. And just a quick example in this slide is what's called the CRAB bundle. So this is bringing together multi-instrument gamma ray analysis from these different experiments. And if you look at the links, you can see more details of this. But you see the various tools. You can have access to the source code. You can have access to the data. There are links to the projects and articles about the projects. But you can also get access to, for example, the Jupyter notebooks, where you can actually run some of this work, and Docker containers are provided. So all of this is accessible from a single environment. Ultimately, this will be visible through the ESCAPE and finally through the EOSC portal. So this particular thing is just an example of how that may look in the long run. And then the other work package I was going to just mention is the virtual observatory. And so this has been something which is an international collaboration, which has been going for quite some time. And I'm sure you all know far more about that than I do. But the importance within ESCAPE is that this is being mapped onto ESCAPE services and eventually onto EOSC services. And the work in ESCAPE is really understanding how to do that mapping and how to make the virtual observatory services consistent and benefit and synergistic with what's eventually in EOSC. Now, to bring all of this together, we are looking at some more integrated science projects, which we've called the test science projects within ESCAPE. And so there are two projects which have been proposed to sort of demonstrate science integration across all of the different ESCAPE work packages. And the idea here is that these actually demonstrate some new science capabilities which make use of the services that we have within ESCAPE. And also should provide feedback on the capabilities delivered by ESCAPE, so you can iterate and improve the thing. And help us really integrate facilities across the project. Now, the two test science projects which are being selected here are both coming from expressions of interest from this GENA, which is the consortium of consortia, which bring together the ECFA, NUPEC, and APEC activities. So there is one project on dark matter and one project on gravitational waves and extreme universe. So these respond to these sort of expressions of interest in this GENA consortium. And the dark matter project is really to bring together all of the many different astronomy, particle, nuclear physics, dark matter experiments, which all looking in different ways at dark matter, and understand how they can really be ultimately hosted on the EOSC, or in our case on ESCAPE, and to exploit the synergies and complementarities across those different communities, using dark matter as a fundamental question, and using our ESCAPE services to bring that together. And one of the things that community is really trying to do is bring together in a common language and common resources, which means things like plots and scenarios, as well as the tools. On the other hand, the Extreme Universe project being to cutting-edge multi-messenger science to understand extreme matter and particle processes. So it's combining various astronomy e-infrastructures and bringing together different data types, bringing together data from different wavelengths, different kinds of astrophysical objects, so that they can really be easily analyzed and modeled together and not done separately. So the idea here is that on trying to do this within the ESCAPE, which we see as a sort of prototype EOSC, we're building a usable and hopefully sustainable multi-messenger astronomy platform. So just to illustrate in a little bit more detail what that means. So if you look at the example of gravitational waves, there are two kinds of phenomena here which are mentioned. On the left is the binary neutron star merger, and you see the different instruments and the different wavelengths which are coming, which are being used to investigate those phenomena. And you have the early triggers from gamma ray bursts and gravitational waves, and then you have a follow-up at different wavelengths over a longer time period. So the keys here are fast alert and localization, and then the longer-term follow-up study. On the other hand, you have, for example, core collapse supernovae, where you have neutrinos and also gravitational waves, and then delayed electromagnetic emission, looking at the mechanisms behind the explosions and getting different kinds of information there. So the idea is to have a platform where these kinds of things can be integrated, where the data can be brought together, and where you can have common analysis projects going on. Similar thing with dark matter. Here there are many, many different kinds of, the example here is on WIMP detection, but there are many different kinds of experiments of different sizes of collaboration, vastly different data volumes. For example, the colliders, as Simone mentioned, you have really multi-petabyte scale data. Other direct detection experiments are at the smaller terabyte or petabyte scale. But there are synergies in the way the analysis and interpretation of results is done. And there's very different ways of working for indirect detection experiments. So the bottom plot you see here is really what's being trying to be done inside the project within ESCAPE, is really to map all of these different pieces of the processes into the ESCAPE work packages, either in terms of data sharing and data processing, or in terms of analysis and preservation and interpretation. So the goal isn't trying to try and do everything in the same way, but to look for synergies and understand whether there can be a sort of broad platform which exploits those synergies, and whether ESCAPE can implement that. And if you look at the comment on the right here, this is from the expression of interest in the JENA, where they make the point that there is no real permanent platform where all of these cross-fertilization opportunities can be done. So one of the goals of this project is to really see whether we can establish such a platform, or at least a prototype of such a platform. So that was the goals of ESCAPE in the near future. Talking about the broader picture, Simone already mentioned this aspect, which is ESCAPE is working with other communities. I mean, as part of the proposal, ESCAPE has to work with PRACE for supercomputing and GEONT for the networking. There is this agreement which was signed between CERN, GEONT and PRACE actually helps us to implement that collaboration. So ESCAPE is building on that collaboration, and ESCAPE is participating in the common demonstrators and work that's being done in that specific collaboration. There are these other science clusters where there are natural, these are very different sciences. We all have a same interest in making sure that the European Open Science Cloud responds to all of our needs. So there are several position statements and common statements on this. And in fact, these 5 science clusters are now working together. There is a sort of regular discussion between the managements of those clusters. And indeed, those clusters are working together inside a new project which has just started, which I'll just mention. This is my last slide. The project is called EOSC Future. It started on the 1st of April. It's responding to a funding call. And the goal is to really bring together all of the previous work that has gone into the various aspects of the EOSC. So you can see this project as really implementing the first prototype of an integrated EOSC. So the outcome of this project should be the first version of EOSC. And the little jigsaw thing at the right here, you see EOSC Future in the center, which is aiming to build the core and the outside pieces of the EOSC implementation. The science clusters, which is the pink thing on the top, you see are bringing these aspects into the mix. There are also regional projects which are working together here. There are other research infrastructures which are not covered by ESCAPE and the other science themed clusters. And underlying it, there are additional new projects which are providing, for example, resource provisioning. And then you see from the sort of chart on the left, the importance as one of the strands of the project, the importance of having these 5 science clusters as part of this project, which are really driving the direction of the project and the structure of what the EOSC will look like. I just mentioned that this block diagram on the bottom right is really how the core of the EOSC is seen for the future. So there's a core technical platform, coordination functions, and horizontal services. And it's these horizontal services which are the migration out of the various communities of things which could potentially be common or multi-use across those different communities. And these are supported by a number of different support functions. So that was my last slide, and I just summarize. So ESCAPE is bringing together these astronomy, astrophysics, and particle nuclear physics communities, building on our common interests in large-scale data management, noting that they're all global collaborations, even though the project is really a European project. And the objectives are really science-driven. There are broader synergies with the other S3 Science Cluster projects, all acting together towards this EOSC, and so we all have aligned goals and common interests there. And actually, now that we have this concept of the science clusters, this is probably something which is going to last for the longer term. So there is discussion on keeping the ESCAPE consortia and the other consortia going even after the project funding may be finished. And the EOSC Future project, which is just starting, will be the first implementation of EOSC. And again, hopefully really driven by the science needs. And that's the end. Thank you.
Thank you, Ian. That's great. There are 3 questions in the Google Doc. First question is from Marcello Asafin, and they ask, what is the total money budget investment involved in ESCAPE's computer network developments? That may be a tricky question to answer on the spot.
So it's impossible to answer. So the ESCAPE project doesn't invest in networking. I mean, I think it's a similar answer to the one Simone gave on networking and the cost of networking. The point is that what we're doing here is really driving networking development, and it's the it's the sort of mandate of the NRENs and GEONT in Europe, and equally ESNet and others in the US and other places, to support our science by doing that development. So there is funding into those activities. It's not directly coming from the science, although some of it comes from the science funding agencies. So I don't think I could ever answer that question.
Okay. Next question is from Knut Olsen. They ask, what challenges are you facing in translating VO protocols into the ESCAPE ecosystem, and which VO protocols are you focusing on?
So I can't answer that. I'm not an astronomer. I think so I know some of the things which are happening in ESCAPE is that SKA, for example, is working with the VO to look at how what is already existing there can help SKA. And I believe some of the other newer infrastructures are doing the same. I don't think it's the protocol. I think it's the, whether the data repositories can be migrated into the data lake, whether there's a match between the software repositories and how all of that work can be integrated into a common environment. So I don't think that anybody's discussing translating protocols. I think it's just a movement of the environment.
Okay, there are a couple of other questions on the document. Robert's put a question in which I think would actually be good for a discussion session, so I'll propose to hold that. And Brigitte has actually said her question is down in the weeds, so I'm going to let you answer that offline if that's okay.
Okay.
I hope that's okay.
I could just briefly say the buy-in from the targeted science community has been pretty good. All of the experiments I mentioned are very involved in the work in ESCAPE.
That's good to hear. Thank you. Okay, our final talk of this session is from Nirav Merchant from the University of Arizona. Nirav is the co-PI on an NSF cyber infrastructure for life sciences, which is more commonly known as CyVerse. So I'm just looking if Nirav is on the call. I hope they are.
I am.
Oh, there you are. I can see you. Great. So I'll hand over to you if you're ready to share your screen. And it says here you've got a 15-minute talk. Is that what you're expecting?
Yes, I am.
Fine. Okay. I just didn't want to rob you of 15 minutes if you're on for the full half an hour. Thank you.
Thank you. Well, thank you for the opportunity. Can you guys hear me okay?
Loud and clear.
Awesome. Okay. So I'll jump right in since I have 15 minutes, and I'm going to try and make sure I stay at 15 minutes. Okay. So our project was born as I planned. This was in 2006. NSF realized the investment going into the bio side of producing data was not being met by the analytics. And so we spent about 2 to 3 years just figuring out what the community needed. And then our mission was to design, deploy, and expand national cyber infrastructure for life science research and train scientists in its use. And the emphasis on train the scientists in its use. In 2013, our mission was broadened from plant sciences to life sciences, and we were continued funding. Some of you may know NSF also has 10 and done kind of mindset, but as we were growing, they realized that our community was relying more on what we were doing, and we grew beyond life sciences, and suddenly the astronomers and hydrologists and transportation engineers started showing up in our infrastructure and building really interesting and cool things. And so over time, our project continued. So we are already beyond our 10-year cycle with NSF. We are into the second year of our third cycle. And in 2019, we started getting larger groups like, groups in Austria and others, which said, hey, we have infrastructure. We want to connect that to make it more meaningful for our community. And so we started giving them, well, everything we do is open source, but we started giving them the services and support to help let them stand up their own infrastructure using our software stack. And so currently where we stand for CyVerse is about 1,600 non-academic institutions, 3,000 plus academic institutions, and over 90,000 registered users globally. Typically, you have labs and groups that produce data. That data is of interest to within the lab and a little bit beyond the lab. If it's a consortium, way beyond that. And then they all struggle with analysis in different ways, but they need some flavor of small compute to large compute, and they keep migrating between them. And eventually their community is well beyond their own lab. And so we need to connect the dots for them. And as you can see right here, what I explained, and this data is eventually needing a lot more scale, but people are not ready for it at times. And then the sharing, as I said, goes beyond their lab and institution. And so that federated ID also becomes really critical. And our data that we help our users with is extremely diverse. We have everything from CubeSat data that comes in to precision agriculture, and I would call that our telescope, where you see that little white box right there. This field is in Arizona, and this robot goes up and down. It's the largest in the world. You can put your own instrumentation in it, but it has its own, and it produces 8 to 10 terabytes depending on hyperspectral 3D, and it literally is watching a plant grow every day, and does a lot of different analysis. And so you can see we go from satellites all the way down to DNA sequences, and the scale of data is varied. The pipelines are different. So a lot of diversity in the data that we work with. So here is a typical announcement for our funding agency. Okay, here's the data release, sharing, and management requirement. It says all software and code must be versioned and should be in GitHub, Bitbucket, and released immediately. Code should be well documented for others to use, and it should be made available through other resources like Galaxy and CyVerse. And I'm always happy when the funding agency names you in a RFP. And it also should be in virtual machines on Amazon or Jetstream, and in containers on Docker and Docker Hub. Now, you would wonder, which is this part of NSF? And those of you not in the US, that's National Science Foundation that pays a lot of our bills for research. And so this actually is from NSF Bio. So this is what they expect from a biologist when applying for funding. And in most cases, that's looking for a unicorn, because expecting all of these skills from a single human being typically is hard, but that's what is becoming the expectation for us. And so our community, and I really like our community because they take these things to heart. So here is a paper from 2020. It talks about annotation tool that they put together. If you read the conclusion, it says, hey, it's developed using R Shiny, it's Python, here's the licensing, and I've put it on GitHub, go get it. And if you want, I've given you a ready-to-use web interface, but if you notice stuff in red, it says, if you want more than 1 gig, no, that's not going to work for you. You need to run all of this on your own. But bless them that they have all the installation details here. As you can see the laundry list, it's not easy. And then that list gets even more complicated. And so then you read their details further, and you realize here is a Docker file available. Go run the pipeline without any dependencies. Now, this is something that you're expecting an average biologist to run for you, and it's not trivial. And so what our users are looking for infrastructure is typically compared to, let's say, a piece of furniture where you feel, it's easy to sit, relax, get your work done, and you want that piece of furniture, and that's the infrastructure you want. And we send them to a place like this. Many of you in the US will recognize this. This is Home Depot, and you're not lying to the user. You're telling them, yes, you want that piece of furniture, that chair. You can go to Home Depot and build it for yourself. There's lumber, there's foam, there's screws, all the tools you need. It's all there. Go build it and enjoy. And that's the equivalent of what we are doing on the infrastructure side. This is a little bit dated version of Amazon. If you log in, that's the Home Depot of cloud. You have aisles and aisles of services, but you better know what you're doing. If not, your furniture starts looking something like this. This is definitely me assembling furniture, extra screws. Or it's fairly uncomfortable. You'll survive, but it's not going to be ideal. And then you have the landscape of other options. While you're working, more and more tools show up. So the new generations of applications are becoming really complex. They have web servers built in. You guys talked of Jupyter notebooks. There's JavaScript libraries. There are databases that go with it. And in our case, the ecosystem is everything from R to Shiny, Jupyter, and it's constantly being extended. And there is no single system that rules it all. There is no programming language that rules it. So we have to be willing to be able to work with whatever comes our way. And in most cases for our users, trying to install this is nearly impossible, and there is software dependency hell. And then we are struggling with reproducibility already. At the same time, the infrastructure, we are getting things from distributed data grids. We are being required for container orchestration. We have to deal with distributed computing, and we have to integrate all of these and provide that as an easy to use application. And then we are expecting our users to know how to manage their data as it flows through these systems. And the most important part is there is no single provider of infrastructure, but a federation. And so you have to be able to stitch it across these systems. And so we are sort of driven by what Alan Kay says, keeping simple things simple while making complex things possible. So that drives a lot what we do in CyVerse. Our platform philosophy is really simple. We try to give cyber infrastructure Lego blocks, and in Danish, that's lagat, which means play well, and also translates into I put it together in Latin. And that's important because we want our users to customize the environment to what is their question. And if the functionality is not there, you craft it by extending what we give you, much like Lego blocks. We give you some fundamental connections that will work. But then if you don't want those and you want to extend them, you are able to do that, and your creativity is not constrained. And so we create an ecosystem of interoperable tools that benefit the broad community and not just few labs. And then we let them manage their digital assets, whether it's in cloud, HPC, containers, just straight up data, and then make sure that it spans their own campus, the national and commercial cloud, without having too much friction at the boundaries of each of these. And we definitely focus on reproducibility, open science, and more importantly, open innovation. And we focus on improving computational productivity. We want to minimize the time our users spend wrestling with the infrastructure. And so one important thing I always like to mention is that CyVerse is not about scaling computation. It's about scaling people, because most labs have that one individual who is really good at what they're doing. And when they build a method or a technique, there are many labs that want to collaborate, but because of the friction at the infrastructure, there's a lot of wasted time, effort, and productivity. And so we focus on making sure that one person can collaborate with 10 more labs instead of one lab. And that comes from democratizing innovation. This is the book by Eric von Hippel, where he talks about how groups that want to share something freely, if they have the right infrastructure, they can do amazing things. And so that drives what we do in CyVerse. At the most foundational level, we take what is available and we add services that are very specific to what our users need. And then we create products and we allow our users to go up and down the stack. So if they want to modify something, they can go down. We provide them the science APIs to modify things. We give them a data store to manage their data. We give them tools that are easy for them to connect HPC and commercial cloud, workflow engines, and things along those lines. We are very much driven by data management for our CI, and it doesn't matter where you want to take your data. We will give you an avenue that's parallel, that's fast, or if you want to mount it and be slow, you can always do that. We do a lot with cloud and containers. Here is an example of Atmosphere, which is sort of our version that sits on top of OpenStack, making it easy. We extended that into Jetstream, which is a much bigger system, again, funded by NSF. You can see login with Exceed, which is our system. And here is an example of a very recent thing. This is a pipeline to analyze SARS virus and assign it to the new strains that are coming out. This was a complex pipeline built by someone, and it was very hard for the community to use. It literally took one afternoon for a graduate student. They built this, they put it inside CyVerse, and now whoever wants to do that is able to do this very easily without having to wrestle with what is a container, how does it work. For them, the question is, I have data that's a sequence with SARS. I need to figure out which COVID strain this is and where it's from. All of that, along with the documentation, is available. And keeping in mind that this is, yes, it's a Jupyter notebook, but not all notebooks are equal. This one needs 16 gigs of RAM. There are many other dependencies. So managing the lifecycle of your container is where the money is, and the orchestration platform. You can only do so much with things that are freely available. For example, we love Binder, but you cannot put your Docker notebook and say, go analyze this on Binder. This is not going to work on my Binder unless you're running your own. But we are very inspired by the work that happens in the My Binder. This is our next generation of work that's coming through Jetstream. And you can see we are now graduated into more, hey, you want a Kubernetes cluster, go get it, and we'll make it easy for you. This is the next Jupyter Jetstream, which it goes live in October. You can see we have it at different regions, again, nicely integrated. And we are now moving our community where they are writing Terraform, where they know how to write those things and connect them. And doesn't matter which cloud provider, whether it's OpenStack or it's commercial, you're able to move things around. And then we focus a lot on keeping our community current. And that comes through continuous learning for humans. You can see here's Container Camp, where we teach how do you design a Docker container or a Singularity container? How do you connect a workflow engine to it? Where do you run it? And how do you have your data show up in the container at the same time get returned back so that it's not a surprise? We are also graduating our community from thinking of machine learning as just a cottage industry, but more like a highly tuned system where you work as a team. So we provide training in ML flow, and how do you take what you're doing in machine learning and focus on working as a team, but think of the life cycle, because end of the day, your model is going to be used by the community. And if you're not going to provide the transparency with your model, very few people are going to rely on it. So I'll end by my most favorite slide, which is coming from an African proverb, which is, if you want to go fast, go alone. But if you want to go far, you go together. And CyVerse is about going far with the community. And with that, I will stop.
Thank you very much. I'm just going to check the questions. I also realize I've got to now look up Shiny, another technology I don't know. So that's one for me. Okay, on the questions, we've got a couple. Robert Nakuta has said, do you know the rough breakdown of life sciences versus non-life science projects on CyVerse today? So everybody was jumping on the success of life sciences.
I would say it's hard for me to give you an accurate number, but if I were to just take a wild guess, it would be about 80% is life science, 20% is other communities. The challenge is we know people exist only when they tell us with questions, but every week something new shows up and we're like, oh my God, you are there. And a lot of them are below the radar because we give 100 gigs of space and they are more than happy to live within that space. So they never ask for more resources, even though we have buttons everywhere. Do you want more? Do you need help? So only when they ask for help do we know who they are. And we do analyze our data in terms of users who are registering, but it's really hard nowadays with interdisciplinary work to put somebody in a department and just assume if they're in computer science, they're doing computer science work. A lot of the life scientists are computational biologists with appointments. And so it's hard to draw a box around people for us.
Okay, there's one more question here from Knut Olsen, who says, I really like your home depot analogy, but it can be hard to anticipate what users really want. How do you balance providing tools for users to assemble against effort spent on anticipating and building what they want from them or what they want for them?
That's an excellent question, Knut. And we sort of divide our group into two parts. One part is people that are already embedded in certain ongoing projects. So these are our what we call science informaticians, and they know the beat of the community and what's happening. So I'll give a very clear example. ML flow was not on our radar 2 years ago. As more and more machine learning projects started showing up, and then people were asking questions, we also had our own work that was happening in that space from other research projects. And we said, we need to make this streamlined for our community. We have the Lego blocks, we have the Kubernetes, we have the Postgres. We just need to connect this and show them how to use ML flow. And that's how that was born. And so it comes from the community sort of bubbling up certain needs. And then we see some things gelling. So we don't try and invent something from grounds up and say, this is what we have created, tada, come and use. We are absolutely not in that space. But when we see 3 or 4 groups gravitating to something, publishing it with that, we're like, hey, there's energy behind this. Let's put our effort behind it and scale it out for more people to use the same tool without having the expertise in that group to do that. Hopefully I've answered your question, Knut.
Thank you very much. There was another question from Robert, which was more about the relative costs of home infrastructure versus commercial cloud. But I actually think that might be another good discussion topic for later. So I'm going to leave that for just now. So I think I've failed my chairship. We are 10 minutes over. I apologize for that, but I think it was worthwhile to spend that 10 minutes. And I certainly enjoyed all of those sessions. I'd suggest we very quickly thank everybody. And if you want to experiment opening your mic, we can try and give them a proper round of applause.
Thank you, everybody.
Or a virtual one. Okay, that's the end of this session. I'll hand back over to Luiz to tell us.
Thank you. Thank you, George. Thank you very much. Just to remind you that we start again at 1:30. The talk that was for now is postponed to 3:30. Ross Thompson's talk, multi-cloud and hybrid strategies for science. Thank you very much. And so please arrive 5 minutes before 1:30 our time, local time. Okay? Thank you.